Welcome to the last lecture of this particular course on thermodynamics, or essentially on the application of classical thermodynamics to biological systems. So in this course or in this lecture I am just going to review whatever we have done in the entire course, and that way it will probably improve some understanding of a few things. If you see things in perspective, it will help a different level of understanding, that is one, and also it is nice to look everything together at one time. This lecture is going to be just speech, or I am just going to continue talking. We probably will not have any gaps in between those nice things that we had when we could reorient and think of something else or do something else and then come back. Those things were used as techniques to improve the learning process itself, bring in active learning and so on and so forth towards the improved active learning process, towards the improved learning process during the lectures. And this is just a review, so we will not have any breaks during the review. The textbook for this course of course was Smith, Van Ness and Abbott. I have given you the edition that I have used, probably there is a more recent edition. And the order of topics I said would be according to the university syllabus, but it will be different from that given in the textbook. The textbook has an order of its own for its own reasons, but for the given university syllabus I think the order followed in this particular course is better for better understanding and seeing things in perspective. The correspondence between the topics covered in the video and the chapter or chapters in the textbook will be available on the course web page, and I had given you an example also for module 2, that the thermodynamic functions H, A and G would be from chapter 6. We are directly jumping to 6 here. Concept of a chemical potential is chapter 10. Equations for a closed systems, Maxwell's relations are again from chapter 6. Gibbs-Duhem equation from chapter 10, and thermodynamic analysis of processes including lost work and irreversibility was from chapter 16. So we would jump about in the textbook, but since you have this, if you want to read further from the textbook you can go to the appropriate chapters and read them. But I think the ordering given in this particular set of lectures would be probably better if you need to understand the various aspects given here. Then I said the approach for the most effective use of thermodynamics that I see here is as follows. We said if you are looking at apples, 3 apples in a basket and you add them with 4 apples, then you get 7 apples. You could see this as 3 apples, if you add them with 4 apples you could get 7 apples. Similarly, if you take 3 coins, 3 10 rupee coins, and add them with 4 other 10 rupee coins, you get 7 10 rupee coins. And so this is in the level of specifics. I could introduce things in the level of specifics, but that makes it very limited. Probably comprehensive approach would be to abstract this into a number 3 and abstract this into a number 4, and we know from first standard mathematics that if you add 3 and 4 together you will always get 7, therefore you will get 7 of that kind. So we said that this is the approach that we are going to follow in this particular course. We will present the abstractions first and then take up specific cases. We said that would make things a lot more complete. Otherwise there are, especially in thermodynamics, and I believe that that is a reason for a lot of confusions in the while following certain ways of exposure to thermodynamics. You take specific cases, then you understand things a certain way which may not be complete, and then you try to apply the same understanding to something else, it will not be valid. Therefore it is best to understand it at the abstract level and then apply it to specific cases, and this is called the axiomatic approach. We will do this, at least I believe in that. And then we talked about classical versus statistical thermodynamics. We said that for biological systems Classical thermodynamics is useful for analysis and design of bioprocess related aspects, some biological relations and so on, even inside the cells, as long as the applications are in the continuum regime. And we saw what a continuum was. It is a situation where there are large number of unitary particles, say molecules per unit volume, and the substance under consideration can be considered as a continuous one. Or in other words, for example, if you plot the density of the substance versus the number of molecules, say in an enclosure, here till it reaches a certain point it is going to remain a constant density, assuming that the temperature pressure conditions are constant and so on, and then after which the number of molecules are so less that its density at a particular point will start fluctuating, you know. So this is the discrete region which we are not concerned with in this particular course. In fact, classical thermodynamics cannot handle that, it can handle only the continuum regime. And to handle this regime, which is very relevant for biological systems, we need statistical thermodynamics, which we will not cover as a part of this course. Therefore, this course will limit itself to the continuum regime. It will define important thermodynamic variables that are fundamental enough. It will also look at ways to estimate such variables, and it will also look at the use of such variables and formulations to predict aspects of importance in biological systems, especially at equilibrium. This was the scope of the course. So with this background, I also told you something about the course philosophy. You know that it is good to know this, to know where exactly I am pitching the course. In fact, we did this sometime in the beginning of the 4th module. Since this is a review and probably the place for this is here, I thought I will present this here. If you look at the number of students in a class on the y axis versus worthwhile achievements, you know, worthwhile achievements does not necessarily mean achievements in an exam. Worthwhile achievements or achievements in a closed book, a closed kind of a exam, in a defined exam or something like that. I am using this to represent something really worthwhile. Then you find that you typically have a Gaussian distribution in a class of a reasonable size, say about 20. This distribution you find time and again. Sometimes the tails are little skewed and so on and so forth, but more or less this distribution remains. I have pitched the course to at this level, at the level of the average, so that the an average student in terms of whatever achievements the person has done, which reflects a certain level of application of that student will be able to get it with reasonable ease. People here of course will feel bored, people here would need to do a lot more work. For people here I did assign an exercise, it could be done over many months and it will challenge your your curiosity and so on and so forth, your whatever you could do, and I will talk about that exercise in a minute. But unfortunately in a situation like this, when it is across a medium, it is a little difficult to handle people here, at least I do not know how to handle this in this particular kind of a medium. In a class what I do is I use cooperative learning techniques where I combine students of different achievement levels together. I have my own way of doing that, I have my own algorithm to do that. I use the group average CGPA is plus or minus 0.25 of the class average CGPA and so on. That works very well for students of lower achievements to pick up from students of higher achievements, and students with higher achievements also get benefited through a better understanding and so on. That typically works well for me here, but unfortunately here I do not know how to do it. To handle people here, I had given an exercise, you can take the exercise for this course also, that is the choose, focus, analyze exercise. Students need to choose a problem of relevance to the bioindustry or any human endeavor and analyze it using the thermodynamic principles taught in class. This is an open-ended exercise which has been designed to improve the skills of choice, focus and analysis in students. A concise report in the format that you think would best communicate your work can be submitted to me at any time and by email, and that would be evaluated on the following criteria, which is originality in approach 15%, focus level 15%, depth of analysis 20%, quantum of work 20%, original contribution 20%, and presentation, which is if I read it once with reasonable concentration I must be able to understand it, that is communication, and that carries 8% maybe, and of course it goes without saying that a shoddy looking report is not professional and therefore it has to look professional, and that will carry 2% for a total of 10%. Okay, those were the preliminaries, and then we reviewed whatever you would have picked up in higher secondary school as well as in your first year of engineering. We reviewed that in one class, and then we went on to module 2. Module 2 was on additional useful thermodynamic functions. We looked at the thermodynamic functions enthalpy, Helmholtz free energy and Gibbs free energy. Then we looked at the concept of chemical potential, equations for a closed system, Maxwell's relations, Gibbs-Duhem equation, and thermodynamic analysis of processes in terms of lost work and irreversibility. We will see some of these as we rush along here in the review. We saw that the consequences of the zeroth law was temperature. It resulted in the useful variable temperature. The consequence of the first law is internal energy, and the consequence of the second law is entropy, and we said that TUS along with P and V are actually sufficient to thermodynamically describe a system, whereas for the ease of use in certain applications, say processes at constant T or P or specific volume, let us define some other thermodynamic properties is what we said, and with that motivation we defined enthalpy as a combination of internal energy and PV. We defined Helmholtz free energy as a combination of internal energy minus Ts, and Gibbs free energy as H minus Ts, and we said the values of the thermodynamic functions U, S, H, A and G, this is a mnemonic based on a name, U, S, H, A and G, have a meaning only if the reference state is mentioned. This is again a kind of a review thing, you know this already. In other words, there is a certain set of conditions at which they are assigned a value 0, and of course one can fix one's own reference state for a particular application. If you are interested in a process, it does not really matter, what reference state you take does not really matter because of this reason, because in a process we are interested in delta U, delta S, delta H, delta A and delta G, delta referring to the value at a final state minus the value at an initial state. For example, delta U would be the value at the final state is U2 minus U reference, taking the reference value along, and the value at the initial state or state 1 is U1 minus U reference. If you take this value, it becomes U2 minus U1 anyway, U reference values get cancelled out, therefore it does not really matter what reference value you choose, but for any of the values at any point to make sense you need a reference value. In fact, you need to know where it has been assigned the value 0. We know that H, A and G, the additional functions, are functions of state, which means they depend only on the state of a system, not on the path taken to achieve state 2 from state 1. And also we said for terminology purposes we will use the capitals U, S, H, A, G and V to specific to denote specific or per mole quantities, and therefore if there are n moles of a pure substance in a system, the internal energy will be Nu, which is also represented as Ut, and I think we finally went with Ut. Its entropy is Ns, the number of moles into molar entropy, or St and so on, and the definitions above Ut, St and so on are all valid for multi-component systems too, since all are extensive properties, and the total property is the sum of properties of individual parts of the system. going by that, we said NH equals Nu plus P times NV, or we are using this terminology, or we use this terminology in the later parts of the course. HT, the total enthalpy, is UT plus P VT. This is intrinsic, so there is no T here. Similarly, AT is UT minus TST, and GT equals HT minus TST. Then we looked at single component single phase systems, and we said we could derive this equation du equals TdS minus PdV for a single phase single component system, and we also recognized that this equation 2.5 contains only state variables, u, t, s, p and v, state variables of the system, whose values depend only on the initial and final states of the system, irrespective of the kind of path followed to achieve state or reach state 2 from state 1. And therefore, we had used some reversible arguments, reversible process arguments to get at this, and we said that this equation is valid for any closed system irrespective of the assumptions that we made regarding the kind of process to achieve this. For example, this could be valid for either irreversible or reversible processes, whereas the interpretation of TdS as the heat interaction is applicable only to a reversible process. The interpretation of PdV as a work interaction is possible only for a reversible process. If you take these two terms separately, then it is not valid, whereas the whole equation is valid for any process. And we had used this nice example of being interested in the difference in heights between points 1 and 2. We said that there could be some paths through which it would be easier to measure the heights as we go along. Therefore, we can choose that path, and for example, probably only on this path an altimeter is available. Altimeter is used to measure heights. Therefore, we could measure heights as we go along this path, and therefore we could measure height here, and in respect of this we could measure height here, and therefore we could get H1 minus H2 or H2 minus H1. Whereas the altimeters may not be available on the other paths, maybe you could take a helicopter and so on and so forth, or trek through an uncharted territory from 1 to 2. In those paths, maybe a way of measurement of the height is not available, but it does not really matter what path you choose, as long as you are interested in the difference in heights. That is going to remain the same irrespective of the path used to go from 1 to 2, and this is essentially a central argument in the ways we went about deriving a few useful relationships in thermodynamics. Therefore, these equations are valid for a single component single phase system, closed system. Du equals TdS minus PdV, dH equals TdS plus VdP, dA equals minus SdT minus PdV, and dG equals minus SdT and plus VdP. And we also said that those are for 1 mole, even if the number of moles increases, as long as it is a pure component system, pure component closed system, you could write the same kind of equations for UT, ST, HT, AT and GT and VT. Proof is given in Den B. Therefore, dUT equals TdST minus P dVT, dHT equals TdST plus VT dP, dAT equals minus ST dt minus P dVT, and dGT equals minus ST dt plus VT dP. Then we looked at multi components single phase system, or multi component homogeneous system. We said N1 would be the number of moles of component 1, N2 would be the number of moles of component 2, and so on. And we saw this very fundamental definition: dou GT dou Ni at constant Tp Nj is defined as the chemical potential. This is pretty much the way it is predominantly used, although there could be other definitions of the chemical potential, because it is much easier to keep Tp and Nj constant while doing an experiment to probably measure this. And also we saw that although the chemical potential has been introduced in the context of a multi component system, it is an intrinsic thermodynamic quantity, a very basic quantity, and it is an equally valid concept for a pure component also. Therefore, for a multi component single phase system, we extended the argument to come up with these equations that are valid: dut equals T dst minus P dVt plus sum over all I mu I dni, similar expressions for dgt, dht and dat. Okay. It is good to have all these things together so that you can always go back and refer to this, and by repeated use you might remember some of these. And then by comparison of the various partial derivatives, for example, this is nothing but dut, dou ut, dou s ds, dou ut, dou st, dst plus dou ut, dou vt, dvt and so on, going by the expansion of the total derivative in terms of the partial derivatives. We could write the various expressions as temperature as this, pressure as this, enthalpy as this, specific volume as this, and the chemical potential as dou ut, dou ni at constant Vt, St and J, or dou Gt, dou ni at constant Tp and J, more commonly used, or dou Ht, dou ni at constant Stp and J, or dou At, dou ni at constant T, Vt and J. Then we derived a fundamental equation, the Gibbs-Duhem equation, which says minus St dt plus Vt dp minus sum over I ni d mu I equals 0. Now this gives a relationship between simultaneous variations of temperature, pressure and chemical potential. And then applying the reciprocity relationship, taking two at a time, and the reciprocity relationship given by the mathematical theorem, we could get very useful relationships, which was dou t, dou Vt at constant St ni equals minus dou P, dou St at constant Vt ni, and so on. I am not going to read those out. They are useful expressions which can be used to represent not so easy to measure thermodynamic variables in terms of easy to measure thermodynamic variables such as Pt and V. And these equations 226 to 231, which we obtained as through application of the reciprocity relationship to equations that are applicable to a closed system, are called Maxwell's relations. This is what I just mentioned. We could represent ut, st, ht, at, gt, which are not so easily measurable, in terms of Tp and Vt, which are easily measurable, by using these Maxwell's relations. And what you will find in a textbook predominantly is Maxwell's relations for 1 mole of a pure substance, and that is this, which you can also get by the earlier relations that we gave, except that we do not consider Ni and T's, the total values and so on, since this is 1 mole of a pure substance. Apart from these, other useful thermodynamic variables or measurable thermodynamic variables are heat capacities. This you already know. Cp is dou H dou T at constant P, or dou Ht dou T at constant P for any system. This is for a pure substance molar value, and similarly Cv is dou U dou T at constant V for a pure substance, or dou Ut dou T at constant V for any system. Similarly, you could also have expansivity and compressibility as useful thermodynamic variables. Expansivity alpha defined as 1 by V dou T at constant P, and isothermal compressibility, as it is called because T is constant here, is defined as minus 1 by V dou P, how the volume changes with pressure at constant temperature, that is kappa. Then we looked at maximum work and lost work. We saw that maximum work could be expressed as T0, the temperature of the surroundings, times S2 minus S1 minus of U2 minus U1, and the maximum possible work for a closed system is this expression. It can be used for making some quick estimates and to evaluate back of the envelope and to do back of the envelope evaluations for claims on certain designs and so on and so forth. If somebody is saying that they can get so much work, you can just quickly do a calculation if you know these values, rules of thumb values, and use that to make a quick decision and so on. Since this is the maximum work, the lost work was ideal or reversible work minus the actual work, and which we derived as T0 times epsilon, which is the entropy that is created. Epsilon is the entropy created. Then we looked at open systems and we came up with an energy balance equation for open systems. This is for the output streams, enthalpy, this is the internal energy term, velocity squared term, and the potential energy term, and the other energies here, and this is for the inlet streams, outlet minus inlet, plus the time variation of the system energy equals Q dot minus Ws dot. And for each of these cases we had worked out examples to see how you can apply or use these expressions in practical situations. Then module 3 was on thermodynamic properties of pure fluids. We first reviewed an ideal gas, we looked at non-ideal gas, Fugacity coefficient, then equations of state or PVT behavior, and various equations of state such as virial and cubic equations of state. Then we looked at generalized correlations, residual properties, estimation of thermodynamic properties using equations of state, and estimation of Fugacity coefficient. Let me just point out a few as we go along this. This was our definition of an ideal gas in terms of the chemical potential, and hopefully you would have realized that this is pretty much the backbone of this course. We have written all in terms of the chemical potential and use that to relate various aspects. Here mu equals mu naught plus RT ln P is that for an ideal gas, mu naught is a function of temperature alone, and ideal gas is therefore one whose chemical potential at constant temperature is a linear function of the logarithm of its pressure. There are some gases, as we know, that approximate well to ideal gases. Most gases do not, they are all non-ideal or real. For them mu equals mu naught plus RT ln F, where F is the fugacity, and to complete the definition we need to say F by P tends to 1 as P tends to 0, and F by P is actually the fugacity coefficient phi. Now the equations of state is nothing but the relationship between P, V and T for a pure substance, and if we define P V by RT as Z, the compressibility factor, then this is one of the virial equations of state in terms of pressure. Z equals 1 plus B2P plus B3P squared plus B4P cube plus B5P power 4 and so on. It is a power series expansion, and you could also write the expansion in terms of specific volumes, and of course that will be in since the pressures were directly related, the specific volumes would be inversely related. Z equals 1 plus C2 by V plus C3 by V squared plus C4 by V cubed and so on, and these coefficients can actually be calculated from statistical mechanics theory. Then we saw cubic equations of state. Now the equations of state, the virial equations can describe the gas phase alone well, the cubic equations can do both gas phase and liquid phase well. You could apply it anywhere, but if you are applying the virial equations, then be a little careful, that is all I am trying to say here, to across states, that is. and the van der Waals equation that you have already seen is nothing but a cubic equation, P equals RT by V minus B minus A by V squared, and A and B are constants for a pure substance. The other popular equation that we saw somewhat extensively in this course is the Redlich-Kwong equation, P equals RT by V minus B minus A by T power 0.5 V into V plus B, and you have expressions for A and B from which you can calculate them. The generalized correlations are come about something like this. We have ideal gas law, we have Rayleigh equations applicable to a wider variety of gases typically, and cubic equations applicable to gas or liquid states of a pure substance with more ease. You could apply this too, but this is with more ease. And now the generalized correlations are something that are applicable to all gases in general, and the generalized correlations are given in terms of reduced properties, which are nothing but the ratio of the actual property to its critical value. For example, reduced pressure PR is P by PC, reduced temperature TR is T by TC, and reduced molar volume is V by Vc. This is the way to write the Redlich-Kwong equation in a generalized form. We went about showing how to do this, and then we looked at the 3 parameter theorem, which essentially says that 3 parameters are good enough, and to use the 3 parameter theorem we have this formulation Z, the compressibility factor, can be written as some Z0 plus omega times Z1. The values of Z0 and Z1 and omega, and I mean omega for a substance and Z0 Z1 under various conditions are given as tables, and therefore this becomes easier to use in the real context. We could use something called residual properties to estimate other thermodynamic properties that are not easily measurable, and the residual properties are nothing but the difference between the actual value and the ideal value. VR residual equals V actual minus V ideal gas, and you could write the residual property for any extensive property USHAG or V, and these are the expressions that we derived after lengthy derivations. GR by RT is integral P reference to P2 Z minus 1 dP by P, HR by RT equals minus T integral P reference to P2 dou Z dou T at constant P dP by P, and SR by R equals minus T integral P reference to P2 dou Z dou T at constant P dP by P minus integral P reference to P2 Z minus 1 dP by P. Therefore, you can use this to get at the reduced value, and if you know the ideal gas value, to get the actual value all you need to do is add them both just by definition, or for a process you could do the deltas too. Then you have a generalized correlation based on residual properties, which is to do that we recognize that P equals Pc PR, and therefore dP equals Pc times dPr. You can do the same thing for temperature, and if you substitute these in the expressions that we had, the residual value expressions that we had derived in the previous slide, shown in the previous slide, you get the generalized correlations in terms of the residual values. So the same form, but in terms of the residual properties. And you could use this same formulation to make it more useful in a practical context. And also HR by RTC is HR naught by RTC plus omega times HR1 by RTC. You have HR naught by RTC and HR1 by RTC values tabulated. That is what makes it easier to use, especially these tabulations are available in your textbook itself. Okay, then we figured out how to get at the fugacity coefficient from the PVT data, and this is the final expression ln of phi1, the fugacity coefficient at 1, is integral of 0 to P1 V by RT minus 1 by P dP. This we had derived, and in terms of the compressibility factor it is nothing but integral of 0 to P1 Z minus 1 by P dP. Then we went to module 4, which was on thermodynamic properties of solutions. Earlier it was pure substance, now it is solutions, which is nothing but mixture of pure substances. We looked at the conditions for ideal and non-ideal solutions in terms of chemical potential, then partial molar properties, excess properties of mixtures, activity coefficient and its estimation. When pure substances are mixed together, there could be changes in volume and enthalpy upon mixing. So that is what makes things either ideal or non-ideal. If there is a change, it becomes a regular solution or a non-ideal solution. If there is no change, it becomes a regular solution. Sorry, if there is no change, it becomes an ideal solution. And then we introduce the concept of perfect mixture of gases. This is, we said, a concept, and we have used this concept quite a few times to develop ideas. A perfect mixture of gases is something for which the chemical potential of each of its component can be represented as mu I equals mu I naught plus RT ln Pi. Pi is the partial pressure, excuse me. Whereas for an imperfect mixture of gases, the chemical potential of each component I is expressed as mu I equals mu I naught plus RT ln Fi hat, which is the fugacity of that component in that mixture. And of course, for completeness, Fi hat by Pi tends to 1 as the total pressure tends to 0. Mu I naught is a function of temperature alone, and Fi hat by the partial pressure of I is defined as the fugacity coefficient of I. For an imperfect gas mixture, based on these definitions, you could write mu I equals mu I naught plus RT ln Phi Pi, which can be, if you expand Pi in terms of P and Yi, you get mu I naught plus RT ln Phi Pi Pyi. Sorry. Now, an ideal solution is one for which each component chemical potential can be written as mu I equals mu I hash plus RT ln Yi, where Yi is the mole fraction of I and mu I hash is both a function of temperature and pressure, the standard value. But in this case, unlike the case of unlike the cases that we have seen earlier, ideal gas and perfect mixture and so on, mu I hash is a function of temperature and pressure. And also note that mu I hash need not necessarily be equal to mu I naught plus RT ln P. And for ideal solutions of liquids and solids, you could write mu I equals mu I hash plus RT ln Xi, where Xi is the mole fraction of the component in a liquid or a solid mixture. In terms of fugacities, it is mu I naught plus RT ln Fi hat, that is mu I naught plus RT ln Fi Xi. For a non-ideal gas solution, we can write mu I equals mu I hash plus RT ln Phi Yi, which is mu I naught plus RT ln Phi Pyi. And for a non-ideal liquid or a solid solution, you have a gamma coming in, mu I equals mu I hash plus RT ln gamma I Xi, and gamma I tends to 1 as Xi tends to 1, which is in terms of the other variables mu I naught plus RT ln gamma I Fi Xi, and gamma I, the activity coefficient, is a function of temperature, pressure and composition. This works well for many liquid solutions, except if the component is of different phases at different mole fractions. For example, at a low mole fraction it could be a liquid in the solution, at a high mole fraction or a pure substance is actually a solid, maybe glucose, or it could be a gas as in oxygen. If that is the case, then we need a special formulation, and that formulation was as follows: mu naught equals mu naught hash plus RT ln gamma naught x naught, and gamma naught tends to 1 as x naught tends to 1 for the solvent, and for the solute mu I equals mu I hash plus RT ln gamma I xi, and gamma I tends to 1 as xi tends to 0. This was the Lewis and Randall rule, where this was powerful because the fugacity of the component in solution Fi hat is nothing but the product of the mole fraction and the fugacity of the pure component, and this can happen only in ideal solutions. This is the Lewis and Randall rule, and since solutions are not ideal, to represent appropriate properties we need partial molar properties, which are defined as dou mt to Ni at constant Tp and Nj. You could define partial molar properties for any of these, and our representation was MIT hash, and the total, this is the reason why we bring about partial molar properties. The total property is nothing but the weighted sum of the partial molar properties weighted with its number of moles, and we had the complete set of partial molar properties here. Total volume in terms of the partial molar volume, total internal energy in terms of the partial molar internal energy, and so on, total Gibbs free energy in terms of the partial molar Gibbs free energy. And then we also saw how to estimate partial molar properties from experimental data. We saw that from mixing experiments, which can be represented as change in volume with a certain mole fraction, you get a curve like this, and if you are interested in the partial molar volume at E, then you take this point on the curve at E, draw a tangent to the point there, the slope, the intercept here Ca would actually give us the difference between V1 T hash, the partial molar property, and the actual property, and the molar property at 1, and since you know the molar property at 1, you could find the partial molar property. And similarly you could do it for the other V2 T hash for a binary system, that is in terms of this other intercept dB. Then we looked at excess properties and also looked at activity coefficients. Excess properties are nothing but the difference between the actual and the ideal properties, the same way as residual properties, where for pure substances we have excess properties for solutions, and we got some useful relationships. Dou Ni of GTE by RT at constant Tp Nj was ln gamma I, and we saw various models: the Margolin model, the Redlich-Kwong model, Van Laar model, and the Wilson model for activity coefficients in a binary system alone. Then we looked at module 5, which was on phase equilibria. We looked at the criteria. If there is one take home message, it is the criteria for phase equilibria from this course. And then we looked at phase rule, Redlich-Kwong equation, and the various equilibria, VLE, LLE, SLE, standing for vapor liquid equilibrium, liquid liquid equilibrium, and solid liquid equilibrium. In fact, we saw liquid liquid equilibrium and solid liquid equilibrium as examples of application of the general criteria for phase equilibrium. This is the one take home message if you want to remember many years after this course. It is this: at equilibrium these conditions need to be satisfied, or at thermodynamic equilibrium you need satisfaction of thermal equilibrium, mechanical equilibrium and chemical equilibrium as given from equations 5, 3 and so on. This says that the temperature of the various phases in equilibrium must be equal for thermal equilibrium, the pressures of the various phases in equilibrium must be equal for mechanical equilibrium, and the chemical potential of each of these species in the various phases must be equal. Mu1 alpha equals mu1 beta equals mu1 gamma, mu2 alpha equals mu2 beta equals mu2 gamma and so on. The degrees of freedom, the number of variables required to specify the state of the system, can be obtained from the phase rule F equals C minus pi plus 2, and this was our Clausius-Clapeyron equation which is valid for phase changes. dP dt equals L, the latent heat for the phase change, by the temperature at which the phase change is occurring, by the change in the molar volume of the two phases. It is valid for any phase change and it can be interpreted as the change in pressure per unit change in temperature that is needed to maintain phase equilibrium. Then we saw conditions for vapor liquid equilibrium from the basic conditions for equilibrium, which was for a single component system it was F, the fugacity of the component in the vapor phase must equal, this is for a pure component, therefore the fugacity of the vapor phase must equal the fugacity of the liquid phase and say that is equal to F sat. And in a multi component system we saw that the fugacity of the component in the vapor phase FIV hat equals must equal the fugacity of the component I in the liquid phase. And in terms of the expansions we could get a useful relationship that phi I pyi equals gamma I fi xi. For liquid liquid equilibrium such a relationship is as follows: gamma I in the L1 phase fi L1 xi L1 must equal gamma I, the same I, in the L2 phase fi L2 and xi L2. And similarly in the solid liquid equilibrium, again from the basic condition that the fugacities must be equal, we get gamma I of the solid phase fi solid zi, the mole fraction in the solid phase, must equal gamma I in the liquid phase fi in the liquid phase and the mole fraction in the liquid phase. Then we looked at the conditions for reaction equilibria. This just follows from the phase equilibria, so this could also be a take home message, summation of nu I mu I equals 0. Then we looked at ways to evaluate equilibrium constant, effect of pressure and temperature on the equilibrium constant, and something to do with ionic equilibria, the formulation for that at least in the last class. So this is the condition for equilibrium, that if you take the free energy, the Gibbs free energy as a function of the reaction coordinate at the condition of equilibrium, the slope of that curve must be 0, and therefore nu I mu I sum over all I, that must be 0. This is the basic condition for reaction equilibrium. And if there are R reactions, independent reactions that take place in a system, for each of those R reactions you could write one such equations. Therefore R such equations will define the equilibrium of that system. For the phase rule, we just saw that the phase rule for a non-reacting system just gets modified by a minus R for a reacting system. Number of degrees of freedom reduces by the number of independent equations in that system. And then we define the various equilibrium constants. I will let you see that on your own, Kp, Kc and Ky, and we also wrote the relationships between the various variables, and this was the temperature dependence of Kp as delta H by RT squared, it was the Fantoff equation, and we could also do that for Kf, which is the equilibrium constant in terms of fugacities. And then we saw the equilibrium constant for reactions occurring in liquid and solid solutions too, as this, and finally some formulations for electrolytes we have seen, which is I will just give you the condition for ionic equilibrium and I will stop there. We also looked at some temperature dependencies, but the condition of ionic equilibrium was mu u equals nu plus mu plus the stoichiometric coefficient of the positively charged species times mu plus nu minus mu minus. Let us stop here, let us stop the review here. I hope that the course was useful, and you can always write back to me if you have any queries. See you then.